All right, AP Statistics students, we're going to go ahead and start our next exam review video. In this video, I'm going to cover Chapter 2, which is the chapter that you learned about z-scores and what they mean and normal distributions. And I'm also going to cover Chapter 7, where we covered sampling distributions. Because what we learned is that if certain conditions are met, a sampling distribution can be a normal distribution. We'll cover that in the second video. So, reviewing Chapter 2. A normal distribution is the name given to a distribution that is supersymmetric. We usually say it's bell-shaped and has the following qualities, which are known as the empirical rule. Approximately 68% of the area under the curve is within one standard deviation of the mean. So 34% of the data is between one standard deviation below the mean, and 34% is between the mean and one standard above. 95% of the area is within two standard deviations of the mean. So there's a 13.5 here and a 13.5 here, making sure that all those numbers add up to 95%. And 99.7% of the area is within three standard deviations of the mean. Now, a word about the empirical rule. If you never remember the empirical rule, you're okay. It's just that the empirical rule can help you answer some questions very, very quickly. So if you encounter, a z-score of -2, you can quickly add up these percentages. But if you never remember the actual empirical rule and how to use it as a shortcut to answer questions, just remember that you can proceed to use the normal CDF command to answer the question just as effectively. Okay, now before we go into our review of the normal distribution, which shouldn't be unfamiliar to you at all because we've been doing it all year, let's talk about a z-score and how we can use it to describe location, not just in a normal distribution really, but any distribution. Please remember that a z-score tells you how many standard deviations above or below the mean a data point is. Remember that z is what we refer to as unit neutral. It doesn't have a unit. Remember on the AP exam and on my test way back then, they try to fool you. They ask you to interpret z, and you find like answer choice A says that z equals 2 means that this score is 2 inches above the mean. And answer choice B, z equals 2, means that you are 2 standard deviations above the mean. Well, you automatically eliminate these answer choices that apply a unit to a z-score. A z-score of 2 doesn't mean 2 inches, even if the problem was given in inches. It means that you're 2 standard deviations above or below the mean. Okay, so be careful with that. Now, how do you calculate a z-score? Well, if you check out the AP formula sheet, you'll see that they have this generalized formula at the top of the second page. It says a z-score is equal to the statistic minus the parameter divided by the standard deviation or the standard error. Yeah, that's a good formula. When you were in Chapter 2, we said that z was equal to x minus mu divided by sigma. So that's score minus mean divided by standard deviation. Then when we moved ahead to Chapter 7 and the inference chapters, the entire second half of the course, sometimes we said, I've got a little typo here, z is equal to p hat minus p divided by the standard deviation. P hat is the statistic, p is the parameter divided by the standard deviation. And then sometimes we said z is equal to x bar minus mu over the standard error. My favorite way of thinking about z is z equals estimate minus predicted divided by standard deviation or standard error. Remember how to calculate z-scores. Now, one thing we learned about when we were in Chapter 2 was how to use z-scores to compare apples to oranges. And what I mean by apples to oranges is being able to compare two outcomes that are in completely different units to see which one is better or worse than the other. They like to go here every now and then in a multiple choice question, or sometimes like part A or part B of a free response question. Tommy ran 100 meters in 10.1 seconds. The average 100 meter time is 10.3 seconds with a standard deviation of 0.1 seconds. Timmy threw the shot put 22 meters. The average shot put distance is 21.8 meters with a standard deviation of 0.2 meters. Which of these two performances is more impressive? Well, you see, it's not a good idea. Oops, sorry about that. It's not a good idea to compare seconds to meters. They're two totally different units. How are you going to compare somebody's running performance with somebody else's throwing performance when the units are not even the same? Well, the answer to that question is we can convert seconds and meters to a common unit called standard deviations or z-scores. So let's talk about Tommy. Well, Tommy's z-score is equal to his run time minus the mean run time divided by the standard deviation. So let's see, that's a negative 0.2 divided by 0.1. I think Tommy's z-score is negative 2. Now, let's talk about Timmy. Well, Timmy's z-score is his score minus the average divided by the standard deviation. Well, let's see, that's 0.2 divided by 0.2, which is 1. So, Tommy's z-score says that he was 2 standard deviations below the mean, and Timmy's z-score says that his throw was 1 standard deviation above the mean. Now, in most circumstances, a positive z-score would be construed as being better than a negative z-score. Like, for instance, if we were doing quiz grades, if your z-score was a 2, that means your quiz grade was 2 above average, 2 standard deviations above average. If your z-score is negative 1, that means your quiz grade was 1 standard deviation below average, which would not be good. But since Tommy is in a running race, a negative z-score is actually a really good thing. It means that he was 2 standard deviations faster than the mean. So we would say that Tommy is the most impressive because his z-score insinuates that he was faster than the mean run, more so than Timmy's throw was farther than the mean shot put. So remember problems like that and be prepared for that. You convert things to z-scores because then those two things can be compared with a common unit known as standard deviations. So now, let's get into normal distribution examples. And once again, these problems should be very familiar to you because not only were we doing normal distributions in Chapter 2, but once we came back in the second semester and we were doing Chapters 7, 8, 9, 10, and 11, normal distributions came back into the conversation. So here we go back to Chapter 2, but this should feel okay by you. The height of male Labrador retrievers is normally distributed with a mean of 23.5 inches and a standard deviation of 0.8 inches. The height of a dog is measured from his shoulder. Labradors must fall under a height limit in order to participate in certain dog shows. If the maximum height is 24.5 inches for male labs, what percentage of the labs are not eligible? Okay, so this problem is asking us to solve a normal distribution, a normal curve problem. Now, if this was a multiple choice question, then feel free to just call up that normal CDF command and punch the buttons, press enter, and select the correct answer choice. But if this was a free response question, what we need to talk about here is what work should you show? Well, when you're doing a normal distribution problem like this one, it can be really a good idea, now that you've completed the course, to define a variable. So you could say, let x equal the height of male Labrador Retriever. And then you can say, what is the probability that x is greater than 24.5 is the question that they're asking you to answer. What percentage of labs will not be eligible? Now, if it's a free response question, there is no question about it that as part of your work shown should be a bell-shaped curve with the center defined. So let's see, we've got a mean of 23.5, and we're looking for the percentage of Labrador Retrievers that are greater than 24.5. So we're trying to find the area to the right of 24.5. So you grab your calculator, and you know that what you need to do is normal CDF, and your lower bound is 24.5, your upper bound is big number, and then your mean 23.5, and your standard deviation, which was 0.8, and you press enter and you get your answer. Okay, now I'm not going to take any time to review that, but I'm going to take a minute to punch this in and get the answer and keep talking about what you should be showing. So let's see, I've got normal CDF up. I'm typing in 24.5 lower bound, some stupid huge number for upper bound, 23.5, and 0.8 for the standard. I'm saying okay. Calculator tells me that that rounds to 0.11-ish. Okay, so if you're in a free response question setting, you should write a complete sentence. Approximately 11% of male labs would not be eligible. So I've defined a variable, I've symbolically stated the question, I've answered the question, I've written a complete sentence, and I have a picture. By the way, you don't even have to show your calculator speak. It's okay if you do, but you don't have to. You're not going to get any extra credit for showing that. Okay? Now, this next problem is very much the same. The heights of mature pecan trees are normally distributed with a mean of 42 feet and a standard deviation of 7.5 feet. What proportion of pecan trees are between 43 and 46 feet tall? You would do this problem the same way as above. Draw yourself a nice picture and label the mean 42. And what proportion are between 43 and 46? So 43 is here and 46 is here. So we're looking for the area in between. So that would be normal CDF, 43 lower bound, 46 upper bound, 42 mean, and 7.5 standard deviation, and get your answer. And write it up just like we did the one above. So I'm pretty sure that you're still familiar with normal distribution problems. Just make sure if you're in a free response setting that you write Do not just circle the answer and not write a sentence. You're not going to get credit for that. Okay, we also learned in Chapter 2 about the inverse normal command, or what we referred to as the backwards problems. Heights of fourth graders are normally distributed with a mean of 52 inches and a standard deviation of 3.5 inches. 10% of fourth graders should have a height below what number? Well, here when they say 10% of fourth graders should have a height below what number, they're saying what height, that should be a 52, sorry, has an area of 0.10 below it. So remember, we have the inverse norm command on our calculator. That's for these problems. And the inverse norm command wants three numbers. The second number is the mean, and the third number is the standard deviation. And on your TI Nspire, the first number that they want is the area to the left. And so in this particular problem, you put the 0.10 there. So let's see, if I grab my calculator, if I press menu, go down to statistics, distributions, there's inverse normal. I'm going to put 0.10 for the area, 52 for the mean, and 3.5 for the standard deviation. I get that this is 47.5 inches. So write a sentence. 10% of fourth graders should have a height below 47.5 inches. Oh, and by the way, I've neglected in this video to remind you the importance of, even if you draw a normal curve, make sure your normal curve has a title. So if we go back up to this problem about the Labradors, we would write heights of male Labradors. You won't get full credit if you don't give your picture a title. So here, above or below it, we would say heights of fourth graders. They're just going to nitpick you if you don't give a title. Okay, so that adequately reviews Chapter 2, and I'm pretty sure you're okay with it. And in the next video, we're going to go to Chapter 7 and talk about how sampling distributions can also be normal distributions.